This is our part 2 video of chi-square, in which we discuss the test of goodness of fit, or when we use the appropriate distribution, or we can say, yes, this distribution or this parameter belongs to the appropriate distribution. So we choose the chi-square test of goodness of fit. So in chi-square test of goodness of fit, basically is an inferential procedure which we use to determine whether a frequency distribution belongs a claim distribution. When one is testing to see whether a frequency distribution fit a specific pattern or not, we choose the goodness of fit test. So in goodness of fit test, if a claim is made regarding a distribution, we can use the following steps to test the claim, like the data is randomly selected, all expected frequencies are greater than or equal to a specific point, no more than 20% of the expected frequencies are less than 5, and the sample is not comprised of observations that are excluded from the population. So if these are the requirements to test the goodness of fit criteria in chi-square distribution. So at the first step, we have to formulate the hypothesis, like the population has a specific probability distribution. And the alternate becomes the population does not have the specific distribution. The level of significance is 0.05. The test statistic is used here and to determine the critical region, which depends upon alpha, the degrees of freedom are decided, and to compute the expected value on the basis of critical region, we take our decision. So these are the steps to calculate the chi-square goodness of fit test. Here you can see the steps are the same like the test of independence. Just the difference in the hypothesis that here we have the population has a specific probability distribution, whereas in chi-square test of independence, we have the populations are two categories are associated, and there is association between two variables. Our two variables are independent, whereas here we have the assumption about the population distribution, probability distribution. So a goodness of fit test required the observed frequencies and the expected frequencies. Here, the criteria to find the expected frequency is based on the probabilities, as we have to test that the distributions come from this probability and not. So expected count is n, size of sample with the probability. So if we multiply size of sample with probability, we get the expected count, and observed is given. So here the degrees of freedoms are k minus 1, where k represents the number of possible outcomes are the categories which we define for the experiment. And this is formula. To calculate this probability, let us take an example. A bank has an ATM installed inside the bank and available to its customer only from 7 to 6 p.m. Monday to Friday. So the manager of the bank wants to investigate if the percentage of transaction made on this ATM is the same each of the 5 days, Monday to Friday of the week. So we need here to test either these 5 days are equally distributed or equally time used ATM machine by different customers. So here we apply the test of goodness of fit. Like here we have the number of users on Monday, number of users on Tuesday, number of users Wednesday, Thursday, and Friday. So at the 1% level of significance, can we reject the null hypothesis that the proportion of people who use the ATM each of the 5 days of the week is the same? So to calculate the proportion of each person, here we can see the probability of 0.2, 0.2, 0.2 for each day. So total probability count is the 1. And total observations here, if we add the number of users, we can get the total users of the ATM of Monday to Friday. So this is our hypothesis that P1, P2, P3, P4, and P5 are equal, which are 0.20. And alternate is at least 2 of the 5 proportions are not equal. So there are 5 categories, as we have the 5 days on which the ATM is used, And in alternate hypothesis, we can say at least 2 days, the count is different. So this is the right tail distribution as this is the chi-square, so left tail. And number of categories are here 5 as we are using the 5 days. So 5 minus 1 are the 4 degrees of freedom here. And the critical value in the area table against the 4 with 0.01 degrees of freedom is 13.277. So this is our critical region, the table value which we calculate from the table. And here are our observed count. These are the probabilities, and expected count can be calculated as n into p. Here n is the 1200 as we have total users of ATM Monday to Friday at 1200. So when we multiply each with the probability, we get the expected count 240 for each day. And this is our calculated value 23.184. Now we have to compare this with our tabulated value. If this is greater than this, we reject. It's not, otherwise we do not reject. So it falls in the rejection region according to the rule. So we reject the null hypothesis and conclude that at least distributions, proportions are not equal. So this is how we can choose the test of goodness of fit. Now the next test of chi-square is the test of homogeneity. So the chi-square test as a test of homogeneity means the populations come from the same variances or not. Each population have the same proportion in the population, have the same contribution. So to test this, we need the test of homogeneity. So here is the example. Let us say telephonic survey, level of agreement with cigarette smoking should be banned in public place. So here are the level of agreement like strongly agree, agree, neutral, disagree, and strongly disagree. And the categories are female and male. Here are their responses. So this is the contingency table 5 into 2. So we can calculate the expected count by multiplying this row total into this column total divided by total number of observations. So we get the first expected 34, and similarly if we multiply 88 into 56 divided by 224, we can get the male count 22 observed. So after calculating these expected frequencies from the observed frequencies, our hypothesis that two populations are homogeneous with respect to level of agreement and two populations are not homogeneous. So this is our test statistics and chi-square with degrees of freedom rho -1 into column -1, which is 2 minus 1 are the column, and in rows we have 5 categories. So we can get the degrees of freedom accordingly. 4 and our at 5% level of significance, we are going to test it. So our table value is 9.488 as we check it with against alpha 0.05 with degrees of freedom 4. So these are our critical region. So here we are the calculation of this, and we make the conclusion accordingly. Either the results or the values lie in the critical region or not. Now let us conclude. So basically, test of independence is used when we have the question, are the two criteria are independent? Are two criteria are associated? Are variables are strong association or not? Have any association or not? So we have to choose the test of independence in chi-square. Whereas when we talk about the homogeneity, it means that are the sample drawn for population that are homogeneous with respect to some criteria? And alternate is that at least one is different. Whereas test of goodness of fit used when we test it, is the sample distribution significantly different from the known population distribution? So we choose the test of goodness of fit. And for test of homogeneity, we choose the population comes from the same variance, and here we test either the populations have the same variances or are they are independent, they have association or not. This is all about the chi-square test. So we have 3 types: test of independence, test of homogeneity, and goodness of fit. Test of independence, we discussed it in our earlier video, whereas in this video, we discussed the detail of test of homogeneity and goodness of fit when we use these tests and how we can do the calculation and draw conclusion accordingly. Thank you.